It's 3 o'clock again, so let's get started. So tomorrow, obviously, assignment 1 is due. So are there any questions about assignment 1? Any trouble? Pretty straightforward? Okay, cool. So you've all gotten the announcement that I posted assignment 2. So it'll be due on the 30th. And so if you haven't seen it yet, it's just basically solving 5 Project Euler problems. So how many of you know what Project Euler is? Okay, so for those who don't know, it's basically a site where you submit a number for each problem on the site, which is a solution to a particular problem. And these problems are not very easy to do by hand, but are much easier to do with the computer. So you're basically exercising your programming and your math skills at the same time. So these problems aren't that difficult. So like the first one is you're basically finding the sum of all multiples of 3 and 5 below 1,000. That should be pretty simple. Then they start to ramp up a little bit in difficulty, like find the largest palindrome made by the product of 2 and 3-digit numbers. And like this one is, so this is just one very large integer written in multiple lines. So it's just one large integer. And what I want you to do is find the 13 adjacent digits, so like 13 digits in a row that have the highest product, and print the product itself. So pretty straightforward. Yeah. And then this one is just the Koyat's problem. So how many of you know what the Koyat's problem is? So it's a conjecture which says that you're given some large number n, and then you obey the sequence that is, if the number's even, divide it by 2, and if it's odd, multiply it by 3 and add 1. And then you keep doing this process over and over and over. And the conjecture is that every single number will reach 1. It's an unsolved problem, it's not proved, but for pretty much all integers we've ever tried, it always ends up at 1. So what I want you to do is, since you are going to be doing this times 3 plus 1, then divide by 2, then possibly doing more things, I want you to figure out what starting number below 1 million produces the longest chain that will reach 1. I can guarantee you that every single number will reach 1, but it's just I want to know what number produces the longest chain. Okay? So that should be a pretty straightforward problem. So, and there's also a small bit of extra credit for each one. Something that I thought was interesting you might want to take a look at. And each one also has a part where you actually write high-level and low-level pseudocode like we talked about last time to help you help design the programming part of the problem. So that part will be even easier. Okay? So any questions about that? Okay, so, and I also posted the list of topics that for your project. So you'll have 2 weeks from yesterday to pick a project topic. And so you can work in groups, you can work by yourself, you can work on any one of these. I actually recommend you only work on one of these because they can be quite involved for some of them, but you can work on more than one if you want. And so I have a whole bunch of difficulty levels, which I think, like some of the easy ones, you might want to do a little bit more than what's listed there. Then medium, I think, is about a good target for what I expect you to do. Then it ramps up in difficulty from there. So the whole goal of the project is not to just look at a whole bunch of algorithms that have been done, but to look at one particular problem or a particular algorithm and go really deep into that. Okay? So any questions on the projects list? Anything that was not quite clear? Yeah.
Is P equals NP on there?
So my advisor told me that he was in. Does anyone know Stephen Cook? He's like the founder of NP Completeness. And my advisor took a class with him a long time ago. And my advisor asked him, like, if I solve P equals NP or not, which is one of the $1 million problems that is still unsolved, what happens if you solve that? And Steve Cook answered him, well, if you solve this, a limousine will appear at your door or at your university, and you'll get a full ride to Stanford a full tenureship, and you'll never have to work a day for the rest of your life.
Yeah.
So I mean, I could put it on there, but
And it'd be fun to research it. It's not like we're gonna be able to solve it, but just to like see where we're at with it.
yeah. From what, so like one of the areas of research that I really like is complexity theory, which is that stuff. And I think, in my opinion, it's going to be one of probably the last Millennium Clay Prize problems to be solved, because pretty much every single direction we've ever taken to try to solve the problem has been debunked. And there are like papers that are posted all the time, like showing that P equals NP. P does not equal NP. We can't prove that P equals NP. Like, there are a whole bunch of things. So, I mean, I could put it on there, but no one will solve it. So, but yeah. So there are 21 projects on here. So hopefully you'll get to pick something that you like, or you can actually pick something that's not on the list. So like maybe some paper that you really like, or some algorithm you really want to look into that's not on this list. You can just get me to approve it, and you can definitely work on something like that. Okay. So anything about projects. So 2 weeks from yesterday, you'll give to me a proposal of your project, and then you can start working from there. So there's that, and tomorrow is the due date for assignment 1. So anything else before we get back into the material? Okay.
One question.
Yeah.
Actually. On the password checker assignment.
Oh yeah.
For taking the file, can we just put that as the first argument, and then maybe with that, or do you want to read it as string?
It'll be the file name will be given to you via sys.argv.
Okay, so it's going to be the first argument.
It'll be the first argument, yeah, and there won't be any other.
Well, after the.
Yes, so it'll be sys.argv1, yeah. But other than that, there's no other arguments. Yeah. So, okay. All right, so we've been talking about algorithms, obviously. So what's an algorithm? We talked about is some finite sequence of steps performed in some specified order, has an entry point, has an exit point. When you're given inputs, it produces outputs. So it's just a mechanism to map an input to an output. How do we represent an algorithm? Well, we have all these programming languages to help us do this, but we turn to pseudocode because it's just a unifying way to abstract away all the details of programming, all the programming languages, and to also incorporate English so that we can read it much more easily. So pseudocode, pseudo means almost, as I said, is a mix of programming concepts in English language. It's to help communicate the purpose of an algorithm much more effectively. There are levels of pseudocode, just as you will be doing in the assignment. So there are high and low levels. So last time we actually talked about 3 different possible pseudocode constructs for displaying all the prime numbers less than 10,000. So the first one is just display all of them. So that's what we came to the conclusion was that that's a high level pseudocode. We came up with one that's a little bit less high level, but we kind of had a few people who said high and some say low level, and that's a perfectly good opinion for this one. For every integer between 2 and 10,000, if n is prime, then print it. So the part that's still high level here is if n is prime, because we know how to implement the rest of it, but that's not quite clear to us yet. So we conclude that somewhere in the middle between high and low level. Then we tried to even go more level, and so we thought that this was a more low level. So there's a function prime. Let's just say it's either built into the language or we made it ourselves. And then we just run a for loop on it and then test every single integer between. Okay? So, and then we just print it if it's prime. So we concluded that's more low level. So how do we implement this algorithm for finding whether an integer is prime? Because the only thing that we need to do is, well, we have the for loop already set up. The only thing that we don't have is finding whether each n is prime. So how do we do that? Well, by the definition of a prime number, it's divisible only by 1 and itself. So every integer, unless it's 2, but if it's some other integer other than 2, every integer between 2 and that number minus 1, that number's not divisible by it. So say like 7, 7's a prime number. It's not divisible by 2, 3, 4, 5, or 6. Okay? So we just do this trial division algorithm. So we assume the number is prime. And then what we want to do is to find a number that between 2 and n minus 1 such that it divides that number. So it's like what we call the witness to whether this number is prime or not. So if the number is even and it's not 2, then it's clearly divisible by 2 because it's even. So we say it's not prime, and then we just stop right there. We don't need to do anything else. But, so once we enter this for loop, either the number is 2 or it's an odd integer greater than 2. Because if it is 2, then it can't fall into that first if statement, but it won't execute this for loop because it's between 3 and n minus 1. N minus 1 is 1, so that for loop will never execute. So the number 2 will say is prime is true, which is good. But for every integer between 3 and n minus 1, we want to check if n divides d, if d divides n. So d is a divisor of n. Then that means it's not a prime number because it divided n. So therefore we set prime to be false, and then we're done. And then if the prime number is true, if the flag prime is true, then we output the number because we never found that witness that said it was false. And then we print it. So how to implement the full algorithm, we had this for loop that will loop between 2 and 10,000. And then we just do all the work in the previous slide for that particular n. And then we are done. Okay? So how do we handle algorithms? We talked about this last time. How do we do this when we're coding? What we do is we split it up into multiple functions. We say, maybe we'll put the prime stuff into one function and then the looping stuff in another function. So we kind of separate all the details from, we don't want our functions to be quite long. We want our functions to be short and simple enough. That can vary depending on who you ask, but short and simple sounds like a good strategy. And we want our functions to do one task, because if they do more than one task, then it'll be harder to, first of all, to name the function, but also the complexity of the function will be quite large, and it would be hard to debug and all that kind of stuff. So why do we want to do that? We want reusability, obviously. We want to use the function in different places. We want readability because we want our functions to be short and to be, for future programmers to be able to see our function. And accuracy, we want to minimize bugs as much as possible. So if we have a short function, the chances of that are very low. All right, so how do we know if an algorithm is correct? How do we go about testing? Well, remember an algorithm has these inputs and outputs. So how many possible inputs could this program take? This program of figuring out whether integer is prime or not, the is prime part. Well, it takes an integer, right? How many integers are there? Infinitely many. So I can't test every single integer to check whether this program is actually correct. So we can't test every possible one. So what we try to do is try to get a heuristic on whether the algorithm is correct or not. And what we do is we try to look at boundary cases. So like at 2 and 10,000, like 2 is the smallest integer and 10,000 is the largest for our program. So we look at those. We look at ones that are around the boundary because we may have an off by 1 error. And then we test some in the middle and outside the range. So we test the smallest and largest prime. Check all possible paths. So this can actually get quite complicated, but if the function's short, it'll actually be quite easy. We'll look at all the possible paths to the program and see, like, if we enter this if statement, then we can say the program's correct. And if we don't, then the program's correct, or maybe it might not be. So by testing all possible paths, then we can be able to check whether a program is correct, or at least get a good heuristic on it. So let's look at the inner loop of our prime function. So what we're going to do is we're going to come up with some good test cases. So for these, for the bounds, the 2 and 10,000, and right around the range. Why is this sufficient? Because we only want a good heuristic. We don't want to test every single integer. We just want a good heuristic. So some of the test cases we came up with were the lowest integer, which is 2. So we should expect that 2 will be printed as prime. Say another one, 97. 97 is a prime number, so we expect that. 100 is divisible by 2, so we don't expect that to be printed. 50 is also divisible by 2, and won't print that. 23 is prime, and we can come up with other test cases if necessary. So now, right at the end of last time, we came up with this brute force algorithm, which is just testing every single possible divisor of n. So we made this function called isPrime, and I called it BF for brute force. So it takes this integer n, and then we have this flag variable isPrime to be set to true. Then we did our check. If the number is even, and it's not 2, then we just outright reject it, and then we just say isPrime is false. Otherwise, it's an odd integer, then we need to do that 3 through n minus 1 thing. So for d in range 3n, so why did I say n here and not n minus 1?
Because you don't need to check the very last?
Well, what does range go up to?
N minus 1.
N minus 1. So it'll go up to n minus 1 for me. So that's why I have n there. Then we check if each of those divisors divides the number. Then if so, then we set isPrime to be false. Okay? And then we just return whether it was true or not. So our input was this integer n, and then our output was a true or false indicator whether the number was prime or not. Okay? So this is our function. So what's an immediate optimization I can make here that you can see? Let's say that we're testing, say, 100. So we know 100 is not prime. Actually, no, that's not a good example. It'd be caught up in the first if statement. So let's say we're testing 9999, so 4 nines. Is that number prime? No, it's divisible by 3, obviously. So we're obviously not going to do the first if statement because the number is not even. So we're going to do the else clause. So it checks from 3 to 9998 whether each d divides this 9999 number. So the first number is 3. So 9999 divided by 3, would that if statement say true? Yeah, so 9999 modulo 3, the remainder 3, is 0, so it'll set isPrime to false. But then what does it do?
It goes and checks every other, so it just returns false?
Well, it checks 4, then it checks 5, then it checks ... And it'll go all the way to n minus 1. But we've already determined that it was false. We didn't need to check every other number, right? Right? So it's checking 4 through 9998 needlessly. So what could I do instead of saying isPrime equal to false there? What else could I do?
Return false.
I can just return false, right? Because I don't need to check every single other number, right? So that's an optimization that we're going to look at when we test our program speed here. But for now, this is just a basic brute force algorithm. Test every single possible divisor. So that's just the strategy of brute force in general. Test every single possible thing that could happen. All right, cool. So the number of steps is O of n because in terms of the value of n. Okay? So why is that? Because this range function goes from 3 to n minus 1, which is about n. So we say big O of n in terms of the value of n. Okay? So yeah, so it's O of n in terms of the value of n. So does anyone not know what the O notation is? Okay, so we're all good on big O notation. Whatever function you have, take all the lower order terms and chuck them out the window. For the highest order term left, remove all constants on it. So like if you have 15n squared or something, you strip off the constants. So the 15 goes away, and then you're left with n squared. So that would be O of n squared, but here is O of n, because I don't want to deal with all the different constants in here. I just want to check, is it a linear time algorithm? Is it a quadratic time algorithm? So it loops from 3 to n minus 1, so that's a linear time algorithm. But do we really need O of n steps? Could we optimize this a bit? So I don't want something like half of n or a quarter n or something like that, because that's a constant that I can just throw away. So I want something that's like much less than n, like maybe log of n or square root of n or something like that. So how can I optimize this? You can actually do square root of n. Why?
Square of n?
A square root of n.
Oh, because that's the furthest it needs to divide.
Right.
To the square root of the number.
Right. So what is the largest possible divisor of n, excluding itself? About the square root of n, well, it's really the floor of the square root of n if the square root is not completely divisible. But it's the floor of the square root of n. But about the square root of n. So what about the numbers, the floor of square root of n plus 1 up to n? Do we need to check those? No, because they can't possibly be a divisor of n. Well, actually they can be, but it's just... actually, no, they can't be. Yeah, they can't be. So we're needlessly testing from square root of n plus 1 up to n. So let's refine our algorithm. So all we're doing now is just we're limiting the search space now. We're still doing a brute force, but we're doing a smart brute force. Instead of testing every single number, we're going to test up to the square root of the number instead. So now I have a new function, is prime. So this is the second attempt. I'm going to still have the same first 3 lines. If the number's even and not 2, I'm going to say false, or I can do a return false also. But now I'm going to do a square root of n with a floor. So I'm calling math.floor and math.square root. So what am I missing from this? Could I use this just as is? Like just math.square. Oh, what am I missing?
It needs to be an integer.
Well, n is an integer, I'm assuming. Yeah, so what am I missing? Purely Python. Something I'm missing. Well, I'm calling math.square root.
Oh, the import.
I got to do an import, yeah. That's the only thing. But this makes sense, right? I just need to do from the floors of the square root of n, and that's all I need to check, right? And then we do our same test. If it divides n, then I set is prime to false, or I can return directly, and then I just return. Okay, just as is. Okay.
Would you not need to do plus 1, n plus 1? Because it's...
Yeah. Yeah, I don't need to do because
you're using the
right, because either square root of n is an integer or it's not. If it's an integer, then the number itself is a square of that number. But if it isn't, then if you round up, it can't. The square of that number will be larger.
I see.
Yeah, so that's the only reason. Okay. So we're going to be testing our program's running time in a second, but after we discuss the next implementation. But this is much faster. So our algorithm is O of square root of n now, instead of O of n, which is much, much better. But what are we testing as divisors now? So we're starting from 3 and going up to this square root thing. So what are the things that we're testing? Well, we're testing 3, we're testing 4, we're testing 5, right? 6, ... What ones are unnecessary to test? Or what, sir?
Even?
Yeah, the even ones, right? Do I need to test 4, 6, 8, 10? No, because if it divides 4, 6, 8, 10, it divided 2 already, which means it would have been caught in this if statement at the beginning. Okay, so we're testing all the even divisors. So they would have been weeded out by 2 before, so we're doing, again, a lot of unnecessary work. So can we skip all of them? So as we talked about when we did the Python stuff, the first argument of range is the lower end, and the second one is the upper end, but we can have an optional third argument, which is the skip, right? So 2 here. So we're going to test from 3 and do a skip of 2 every time. So we're going to test 3, 5, 7, 9, and so on. Okay? So this actually doesn't improve the asymptotic running time, so it'll still be square root n. But here, I'm going to do half the work because I'm effectively removing half of the numbers I have to divide by. Okay? So let's do everything as before. So now it's my third attempt. I'm going to have the same first 3 lines. But here, now I'm just going to add that comma 2 at the end. So I'm going to only test 3, 5, 7 up to the square root number. And so if it divides, then set prime to false, then return. So it's almost exactly the same, but just one minor change made this algorithm run twice as fast. Isn't that cool? Cool. So let's see. So if we wanted to implement this in Python, we wanted to test from 2 to 10,000 because these algorithms are just testing the primality of one number instead of a whole bunch. So if we wanted to test from 2 to 10,000 and just print those, what we would do is we would run from from 2 to 10,000 plus 1 because it's exclusive on the upper end. So we're really testing the 10,000 here. So if the prime function that we're considering is true, or is prime 2, but I'm doing is prime 3 because it was the fastest one, then we print the number. And then I added the named argument end to be a space. So because I don't want 1 on each line, I just do it separated by spaces. And then a print for a new line at the very end. So we can do some test cases. So this isn't the way to actually do test cases in Python, but it's just an easy way to understand how to do test cases. So I'm making a function which takes, t, I can pass functions around between other functions. So t will be one of the functions is prime bf, is prime 2, or is prime 3. And n is the integer that I'm going to pass to each one. So I'm going to be testing. So when I pass t here, it's going to print the function location in memory. There are ways to actually print the actual name of the function here, which is kind of cool. So I'm going to be testing that. Sorry. I could do that, or I can do t to be the witness. So it could be the witness of whether n is prime or not. So you can either do that, but I can also make a method which will run each of the test cases. So it'll run test case 1, which will test 2. Test case 2 will print 90. We'll do 97. 3 will do 100, and I can make test cases this way. And then because I may want to use this in another module, I don't want to run the actual program if I want to import it from somewhere else. So what did we do? Well, we had this this dunder name thing, this double underscore name. If it's equal to underscore main, then that means we were called from the Python 3 interpreter. So that means we're really doing the main function instead of importing it. So we can actually pass flags in sys.argv. So how many of you, when working on the command line, have used flags before? So like a dash something. So yeah, so a dash here means you set a specific option. Again, this is not how it's done in Python. There's a much better way. But I'm just saying if you have a flag in the list of arguments, then you can delegate a certain functionality here. So if I pass dash t, then I can just run test. Otherwise, then if I didn't pass the test flag, then I can just run the main function itself. Okay? So so if I try to run this, then it'll print each of the numbers as necessary. And if I pass in the t flag, then I'm going to print each of the test cases. Okay? So any questions about that? So let's actually not just talk with my hands waving and saying this algorithm's better than this other algorithm. Let's actually see how much faster it really is. So we actually talked about those 3 functions. This is prime brute force, the second attempt where we only go up to square root n, and the third attempt which did every other divisor instead of doing every possible divisor. But we also talked about how we can return directly instead of testing every single other divisor from 3 to whatever one we're considering. So I have really 6 functions now. So our normal is prime bf, brute force. But I also have another one which is the same thing, but I'm returning right when I have a determination on whether a certain number's false, yeah.
Sorry, you don't need the and not equals 2, right? Because as soon as you hit the 2 mod 2, it's going to return 0, and then...
Well, if I just have this, then 2 will return false then. 2 is a prime number.
But that statement will return true, which will put it in, which will return false, right?
Yeah,
oh, I see what you're saying.
Yeah, I need the case for 2 to be out of there, but otherwise, most of the time it'll hit this and mod 2, but only in one case will it hit this and not equal to. Okay, so we have this return early function. Then I have our second attempt, which did up to the square root of n instead, and also a return early version of that. And then our third attempt, which did every other divisor, and also a return early version of that. So what I'm thinking is that this return early function for our third attempt should be the fastest one, right? Because it's doing the fewest possible divisors, and it's returning early, and it's doing the fewest possible divisors. Okay, so what I have here is a main function, which will, what I'm doing now is I'm running up to 100,000. Actually, I should just do up to 10,000 to match our example. So what is this result equals bracket 0 times size doing? Well, when we, obviously the times operator is overloaded depending on the context. So like for 2 integers, it's the multiplication. But for here, it's like strings. So it's a list times a number. So what that means is repeat this element and make a long list the size of size with a default element set to 0. Okay? So what this will do is, so I'm passing f. F will be the function that we're testing at that current moment. So it'll be is prime bf, then is prime bf return early, then is prime 2, etc. And so actually, since we're actually not using result here, but what I'm doing is I'm just running the function from 2 to 10,000, right? So I'm testing the range from 2 to 10,000 because it's exclusive on the upper end. And then I'm just calling f on each of the integers in between 2 and 10,000. So what I'm going to be doing is I'm going to be testing this main function for each of my 6 functions. Okay? So the way we do time, like if you want to time a particular function in Python, is with the timeIt module. So I have another function called timefunc. So what will be happening in timefunc is it'll print the amount of time it took for the passed-in function f. So I pass an f to timefunc, and what I'm going to do is I'm going to run this main function 5 times, because if we run it one time, it may run really quickly once and then really slow another time. So what I'm going to do is I'm going to run it 5 separate times and then take the average of each time, which would make it a good estimate. So the way you do that is I set the number of times. I can change this number if I want. Then I create a timer from the timeIt module, and then I create a lambda. So what does lambda do? Does anyone remember what a lambda does? I didn't actually cover it, but
Can you
just
say what's called like a generalized function to like be the things go?
right. So what a lambda is just a function with no name. Okay. So lambda is just like a function you can write in one line here. So what this lambda does, it takes in no argument, so there's no argument specified here, and then it'll run main on this passed-in function f. So this timer will take a function in and then run the function, return the time to me. So what I'm going to be printing here is, because I said everything in Python is an object, so even functions, you can call really cool things like the name of the function. So what this double underscore name will return is the string, which is the name of the function itself, which I think is pretty cool. And then when you call the timeIt function on the timer itself, there's a named argument for the number of times the function runs. I believe the default is 10, but I'm not sure of that. But here it's going to run 5 times, and then it'll run those 5 times and then return how long it took to run all 5 times, and then I just normalize it by how many times I ran. So this will give me the average of how long it took to run f on main. So if I uncomment these, so the reason I commented them was because I was playing around and I set size to be 100,000, and brute force took way too long to do. But we'll see that in a second. So let's actually just run 10,000 for a second. So what we're going to do is we're going to print brute force, then run the brute force algorithm, and then as well as the return early one. Do our second attempt with the return early, third attempt with the return early. So any questions about this before we run? Okay, so I'm going to put this over here, and then Python 3 primes. All right, so it says that on average, brute force ran in 4/100ths of a second, and return early ran in 1/100th of a second. So obviously, return early is going to do better. But is prime 2 was about, I guess, 20 times faster. And then return early was even twice as fast as that. And then is prime 3 was about 1,000th of a second. And then return early, not quite half as fast, twice as fast, but it's about 1,000th of a second. So you're thinking, well, these are really short times. I want to see a really long time and a really short time. So what do? Make it run longer. Okay. So what I'm going to do is I'm going to set size to be 10,000 now. So if I run now, brute force will take a little bit more time. So now is the moment when we should play the Jeopardy music, because it actually takes a little bit of time to run. But don't worry, the second and third attempts are much faster. Yeah. So is prime brute force ran on average 4 seconds. So return early ran in about a second, so it's about 4 times quicker. Is prime 2, instead of running 4 seconds, it ran in 1/20th of a second, and then return early was a little more than half the speed. Twice as fast. And is prime 3 was even faster. And you can see by here it's about half, because this is 1.6 milliseconds and this was 3.2. So it's about half, which is what we would expect because we test half the divisors. So now you're thinking, well, I want to see the 2 faster functions run even longer. But the problem is that we'd be here all day testing brute force. So I'm just going to comment that out, and then we'll run again. So we'll see how long this takes. So is prime 2 was about 1.7. So return early was about 3-4-ish times faster. Is prime 3 was about half, because that's what we would expect, because it's half the running time of the first one, because we test half the divisors, and return early was even faster. Okay? So any questions on that? So we use the timeIt module to test a particular function's runtime, and we can pass functions along so we can test a particular function. Okay? So any questions on that? Okay. So yeah. So this is our implementation. So I did a different implementation than was on the slides, so I'll share both of them with you. But I just did another way to use the timeIt module to test how long a particular function took. So what we want to know in analyzing our algorithm, so we said it ran in O of n time, and then our second and third algorithms ran in square root n time. So the way we want to figure out whether a particular algorithm is fast or efficient, how do we do that? You can compare test cases, but I meant like looking at the algorithm as a high-level algorithm. Like when we said O of n time and square root n time, how do I know the square root n is faster than the n time? Because square root n is way less than n, right? So we use what we use is this O notation, right? But when we did this faster algorithm, what was our metric for determining this second and third algorithms were better than the first one? We said it was better. Yeah, it was time, right? So could we think of another strategy for figuring out whether an algorithm's efficient or a fast algorithm? Yeah, amount of memory used. What's another one? Another one may be, well, anyone know what a solid-state drive is? Yeah, so a solid-state drive is basically like a hard drive, but it has no moving parts, so it's much faster to read and write. But there are some reports that writing to a solid-state disk, or even a hard disk, is much slower than reading from a disk. So we may even think about algorithms that have fewer writes to maybe memory or to a hard disk or something like that. So there are many ways to classify algorithms. It's not just for time, but it can be also for space, the number of math operations. So it turns out that this modulus operator, this percent, is very, very slow, even on modern processors. In some cases that I've heard, even a conditional branch, like an if statement, is faster than a modulus operation. So we can classify algorithms that way. So the most common approach that most people want to care about is the number of steps that are taken, or more colloquially, the amount of time that's taken. So how do we rank an algorithm versus another algorithm? Well, we talked about that. It's use O notation, right? So if we did this process of removing the lower order terms, drop off all the constants, and then compare algorithms that way, we see that one maybe is more efficient asymptotically. So this suppresses all constants. So I may have an algorithm that runs in 1,000,000 square root n time, but I have another one that runs in 2n time. The 2n for most purposes will be faster, but asymptotically it's slower. Okay? So there's a difference between an asymptotic running time and the actual running time. So the actual running time is obviously the profile and to test your functions, see how long it takes. But for asymptotics, we use O notation. Okay? So are there any questions about that? Okay. So ready for a big lie that you've been told? So this is the function. So here's our algorithm, the third iteration. So it's our fastest one. So the first three lines obviously take O of 1 time, right? So it's a constant amount of operations. So setting a variable takes constant time, setting a variable takes constant time, and constant in a sense for testing whether it's equal to 2 and doing whether it's even or not. So there are much easier ways of doing this than just dividing and then taking the remainder. So what's an easy way to test whether something is divisible by 2 or not? If I want to avoid actually doing a division. Modulo actually does a division on the back end. Well, one thing is, it's actually special to 2. What you do is you look at the binary of the number. What is the last digit, the least significant digit? It's either 0 or 1, right? If it's 0, then that means it's divisible by 2. So I can check in constant time by just looking at the last element. So you really can do these in constant time. So the inner body of the for loop is constant time, although it's constant in a sense. So this could be a cool project idea. You can look at algorithms like this, for like testing a divisor or something. What is the actual running time of that? It's not O of 1, because what you need to do is, if it's not 2, then you need to actually do the division itself. So how long does division take? Well, first of all, you need to read the whole integer n. Obviously, you need to read that integer n. And you need to do a division and write the result out to memory. So that's not a constant time algorithm in terms of n. We just say it as constant because because it's one operation. So what we usually classify algorithms as a certain number of operations, like O of n operations, instead of O of n time, because an operation might not be constant time. Okay? But that's not the lie yet. The for loop obviously runs in O of square root n time because we run from 3, skip every integer up to square root n, so it's about square root n over 2. But as I said, O notation suppress constants and then just take the result of that. Okay, so the whole algorithm runs in square root n time, right? Because the first part takes constant time, and the last part square root n operations and O of 1 operations in the loop. So square root n times 1, I think that's square root n. Okay? So are there any questions about that? Prepare to have your mind blown. But this is not how it's actually done. So you've been told a lie, your whatever class you found this out in. So what we measured the runtime of the algorithm is the value of the input, of the value of n directly. But what algorithms are actually measured against are the size of the input, not the actual numerical value. So let's see, so in terms of n, how many bits do I need to actually write down that number, n? How many?
8. You mean the actual decimal value?
If I wanted to write down, say, the binary number. Well, what's the highest power of 2 that n could be? What's the highest power of 2 for which it equals n? Well, it's about the logarithm of n, right? Like 2 to the log n, that's just n, right? So it'll take me about log n bits to write down. Well, I'm suppressing constants because if you use, say, base 10 or base 2, if you know a little bit about how logarithms work, that's just changing constants. But there's this special base called unary, which is base 1. So if I write down, if I wanted to write down n in terms of unary, it's just 1, 1, 1, 1, 1, 1, n times, right? So it's not the same thing as binary. So in this one special case, the size of n is actually n. But for every other base, like 2 and up, you need O of log n bits instead of O of n. That's how it's actually written down. So this algorithm is tested against the size of n, not the numerical value. So it's tested against log n. Okay? So so we have a log n size input, and the running time is square root of n. So the size is log n, and the running time is square root in the value, not the size. So it's not a square root time algorithm anymore. This is an exponential time algorithm. Why is that? Why is this an exponential time algorithm? Well, what's 2 to the log n? It's just n, right? 2 to the log n is just n. But our algorithm ran a square root n. So this is really square root of 2 to the log n, right? But another way of saying that is just 2 to the power n divided by 2, right? Because if you are doing a square root, it's just dividing the exponent by 2. So this is really 2 to the n divided by 2. But that is also an exponential time algorithm because it's still a number to n. So that's still an exponential time algorithm. This isn't an efficient algorithm at all. We thought it was efficient, right? But let's say that we're dealing with the problem of searching for a value in an array, and we say that runs in O of n time. That really does run in O of n time. Why is that? Remember, we're not testing the size of we're not testing the value of the input, we're testing the size. What's the size of an array of size n? N, right? So we're doing, it's not really constant, but let's just say constant work for each element. So n times a constant number of work, that's O of n. But here, the difference is you're measuring against, it's not really a difference, but what you need to consider is we're testing against the size of the input, not the value of the input. So this is an exponential time algorithm, not efficient at all. Even though we did all that work just to try to make it more efficient. But there is a polynomial time algorithm. So how many of you know what polynomial time is? So what that is O of n to some number. So like O of n squared, O of n cubed. Those are called polynomial time algorithms. And those are usually considered or classified as efficient algorithms. So our algorithm as is not efficient because it's not polynomial time. But there is a paper that was released, I think, 14 years now ago, and I proposed this as a project idea. So you can see, you can look at, well, now they actually made a polynomial time algorithm in terms of log n now, not in terms of n. Okay? So any questions about this before we take a break? I know we need a break. Okay, let's take a break. 4 o'clock, so let's pick up where we left off. So I was finished telling you the big moment of truth, what is actually done in algorithms. So we measure algorithms in terms of the size of the input, not in terms of the value of the input. Because if I change the value, then it might change the size. And what we expect of algorithms is that it'll run longer depending on the size of the input instead of the actual value. So we talked about how other than base 1, we need to represent a number using log n bits instead of just n bits. Since the input is log n in size, the algorithm runs in exponential time. And there are algorithms for polynomial time for checking whether a number is prime or not. And actually, interestingly, it actually is true that since you can do this for testing if a number is prime, you can do it whether it's composite. So a composite number is whether it's not prime. But we do not know of an algorithm for factorizing a number into its prime factors in polynomial time. We don't even know of an algorithm to do that. But we know how to do whether a number is prime or not to verify it, but we don't know how to produce the factors in polynomial time, which I think is pretty strange, but such is the world of algorithm analysis. Anyway, we want to know efficient algorithms because we want to implement efficient algorithms in whatever application that we want to do. Because they take less time than inefficient algorithms in general. We talked about various types of measuring algorithms against other algorithms in terms of the actual running time itself when we test on a particular test case. There are the asymptotic running time as well. We can compare asymptotic running time before we actually implement it for a really large input. We talked about other ones like the amount of space that's taken, the amount of times it's written or read from a particular source, such as like a disk. So there are many ways to classify algorithms. Scalable algorithms, which means efficient in terms of the size of the input, that's what we want. So what do we need to know? There are many, like hundreds, literally, of ways to classify what an operation is, how long a particular algorithm takes. So what we usually denote a mathematical operation like divide or addition, we can do in constant time. Even though, say if we have two numbers, n and m, well this one, n, takes log n bits to store, and this one takes log m bits to store. If we wanted to add them, then we need to examine every single bit of both of them, which means we need to do this in the larger of the two integers log time. So let's say it's n. So addition operation can actually be done in it won't be constant time here, but we usually just abstract away the details because since its log n is so small compared to probably the other parts of the algorithm, so we don't even consider that. But sometimes you actually do consider it. So what we usually consider the running time of a loop is if the inner body runs in a certain amount of time, let's just say it's O of B, and then the number of iterations is O of A, then we just multiply them. So this one's actually correct. If you know the runtime of the inner body and the number of times it's the loop is executed, then we know the running time of the entire loop. So this one's actually correct. Numbers are represented by log n bits. Sometimes you actually don't care about the size of the integer, but like in this prime example, since that was the only thing that we're measuring against, we actually do care about it there. Another one that you could care about is the running time of multiplying two numbers. So the standard algorithm will run in the square of the size of the input, and there are algorithms which I propose again as a project idea that run faster than that. But we measure it against the size of the input instead of the actual value. Algorithms run in some function of n time, where n is the size of the input that's given to the function. So any questions about analysis of algorithms? So there are whole courses on being able to just analyze an algorithm. And so like you may determine that a particular algorithm runs in, say, 3 to n times, so just some constant to the n. Even just using more sophisticated analysis techniques, not even changing the algorithm, you can actually reduce the running time. So even analyzing algorithms is a very difficult thing to do. So that's why it's important to be able to analyze algorithms correctly. Try to be able to see how does the function behave in terms of the size of the input that's given. So this is my handy guide to design an efficient algorithm. Although it doesn't work in all cases, it's just a general way to approach this. So define the problem, figure out what you need to do, what are the inputs and outputs, what's the size of the input, obviously, that you need to know. Abstract any and possibly all details that are unnecessary for the algorithm. So maybe like, maybe we don't need to have that case where we needed to check whether the number was divisible by 2 or not before that, because we could have just ran the for loop on that one anyway. So we can just abstract away details that are unnecessary. It'll just make the analysis easier. Because I didn't need to look at that O of 1, in a sense, work at the beginning for checking that even number part in our prime example. User program is a subroutine for another one. So as we talked about, divide up your functions into smaller functions as necessary, and then use each one as a subroutine in another one. Why would you want to do that? Well, if we know the runtime of some function and I use it somewhere else, then I know that line, the running time of that one line, right? So it's not just this big complicated thing. I know I can actually get better at estimating this other function's running time because I know that one line. Okay? So it's just like using each function as a building block for analyzing the running time of another function. Use creativity. So we use this for our prime example. Instead of just testing every single integer that could possibly work as a brute force, we tried to be creative and try to remove every single integer that we know will not work, and it's just a redundant check. So using creativity, just try to figure out for a particular problem, and this is problem specific, what things you can eliminate from searching to reduce the running time or the space used or things like that. Analyze the program's scalability and efficiency. So what is the running time of the algorithm? And actually testing it. So for these small inputs, it runs in this time. For these large inputs, it runs in this amount of time. Does this scale well? Okay. So this is just a check. Did the other steps actually help me in reducing the running time, making this an efficient algorithm? Evaluate the performance by actually implementing it in some programming language like Python or Java or something like that. And then repeat. Just keep doing this and then try to iteratively make the algorithm as efficient as you can. Okay? So any questions on that? Okay. So for takeaways, pseudocode's important, but sometimes it may be difficult to model it, but pseudocode is important to understand how a particular algorithm behaves. It's easily translatable to source code, though. Once you actually have pseudocode, you can write the program to do it on the actual computer. Testing is difficult. So coming up with the actual test cases are very difficult. There are whole research areas on figuring out what are the best test cases to do. And it's actually a very open research field. But if you can actually find good test cases, it saves a lot of hassle. There's a lot of things that you won't have to test. You will know that they're correct based off the test cases that you gave it. Algorithm design is very important because being able to just figure out how you're going to design the algorithm before you implement it will save you so much time. Trying to be able to figure out what are the parts that I can remove? What is the structure of how this program's going to operate? That's what's really important in algorithm design. Trying to figure out whether one algorithm is better than the other. Well, I can just use the more efficient one if it already exists. There's no point in reinventing the wheel. So algorithm design is incredibly important. All right, so this takes us to a little bit of a detour to what I call recurrence relations. So how many of you know what a recurrence relation is? So what it is basically, obviously we know what recursion is, right? Anyone not know what recursion is? All right, so basically if we call ourselves, then that may affect the runtime a lot, right? Because we could have this function which does some stuff, and then we call ourselves with a smaller input, but we don't know the running time of ourselves because we need to know the running time of ourselves, right? Because for this for this recursive call to ourselves, we want to know the running time of that, but that would solve this running time of this algorithm that we're already making. So what recurrence relations do are to be able to solve this in terms of when we have recursive calls. So it's just a way of analyzing the amount of time or space, some measure that we're considering, used of a particular function that allows to call itself. So it does a recursive call. So what we usually denote as the runtime or the space used of a particular function, we call t of n. So t is a function of the input size, which is n. And so suppose that the algorithm splits into two pieces. Actually, that's a very big typo. The algorithm doesn't split into two pieces. The input splits into two pieces. So it should really say if the input splits into two pieces. All right. So let's say that it splits into two pieces, and then we recursively call the result on each. So this is kind of how merge sort works, right? So you use, given this unsorted array, split it into two pieces, recursively call on each piece. And then when we stop, when we get down to one element, and we have two arrays with one or maybe two elements, then we merge them together. And then we go up one level in the recursion, merge those together, go up again, until we get to the final original call, in which case we have two sorted arrays of length n over 2. Then in place, merge those two arrays together. Okay, so that's just how merge sort works. So this is just basically an abstraction of that. You split the input into two pieces and recursively call on each. And then to join the result, because we have two pieces of n over 2, we need to look at every single part of those n over 2 pieces. And so it takes O of n time to join those two recursive calls back. So what we do is we model this as, well, I don't know what the running time of this function is, but I know it's t of n. So I want to express t of n in terms of itself because we did those recursive calls. So we have two recursive calls that we made on each of those pieces. And so we have two recursive calls to t of size n over 2 because we split it into two pieces. And then once we did all that, we took O of n to join them back together. So this is just another way of looking at recursive algorithms and trying to determine the running time of that. So this isn't an expression which says t of n is O of some function. So what we want to do in recurrence relations is we're given this recursive call function structure, and we want to figure out what is the closed form expression of this. So we want to say t of n equals O of some expression. Okay? Instead of, I don't want a t on the right-hand side. I only want it on the left-hand side. So it's not quite clear, since these are functions, how to do that directly. So I want to solve t of n explicitly without actually doing the recursion. So how do you think we solve these in general? There actually isn't a way. I actually put this on the project list. There's one recurrence relation where no one knows the explicit solution yet. So if you can find the explicit solution, it'll definitely be a publishable paper. If you can solve this recurrence relation I have on the paper. So there are recurrence relations we don't know how to do in general. There are some recurrence relations where we only know one way to do it, and then there's some that we can do many ways for. So there's no one method that'll solve all of them. But it'd be nice to know just a few of them. How do you solve these? How do you solve at least a lot of these? So there are a couple techniques. So any best technique? One technique literally is to guess. It's just to guess a solution and then confirm it. So how many of you know what induction is? So induction is, so we guess a solution. Let's just say we guess a solution. Like for that 2 times t of n over 2 example. So what we do is we guess a solution, say n log n or something, or n squared. So what we do is, by induction, so what induction is you look at a base case and then verify that it's correct for one base case. Then you assume for some number k that it's true up to that point. So like it's for true up from that base case up to k. Then you prove the case for k plus 1. Okay? So if you can prove everything from k1 to k up to k plus 1, then you can prove it for all possible input sizes. Okay? So that's just a quick introduction to induction. Introduction to induction. All right, so another one that is taught in 310, CSA 310 much more formally, which is called the master method. So by the name, it implies that there are many, many recurrences that will fall into this category. So obviously guessing won't be effective in some cases. It might be very difficult to guess, but the master method is a really good way to explicitly get a solution that you want. And there are more complicated ones. So this is a project I put on the list, so to look at some of the more complicated routines. So let's look at the first two. Project idea, look at the proof. So I'm not going to do the proof of the master method because I'm going to save that for 310. But if you wanted to look at this project, then you can look at that proof of how the master method works, as we're going to get to, and some of the more complicated routines. And actually, it's really cool. Some of the routines involve calculus. So if you're good at calculus, you should do that one. All right, so guessing. So we have the recurrence relation we did before really is the one for merge sort, right? Because we have this unsorted array, split it into 2 n over 2 pieces, and then when we want to combine the result, we got to create a sorted list from these 2 sorted lists, and that's just one pass over each of the 2 n over 2 arrays, which takes n time. So I can actually drop the O of n here. I can just say n, because it actually is n here. So, but the recurrence stays the same otherwise. So one way of guessing is to unravel the recurrence. So this is one level of the recursion, but we can substitute the result for t of n over 2 in place where t of n over 2 is. So we can unravel it and see what are the patterns that occur over time. So let's say that this is our recurrence as before. So if we plug in t of n over 2, well, that's just 2 of the right-hand side of what t of n over 2 is, which is just divide wherever the n is, divide by 2. So instead of 2t n over 2 plus n, now it's 2t of n over 4 plus n over 2. Okay? It's just unraveling the recurrence once. And then once we settle the math, we find that we have 4 copies of this n over 4 a recursive call. And it's actually quite cool figuring out how these constants end up, because it's basically 4 recursive calls on each of the 4 n over 4 size sublists. So there are 4 lists, and we recursively call on each. But why is it 2n here? Well, it's basically looking at what when we get to the top level the recurrence is actually doing. So what's the top level? It takes each side of these n over 4s, puts two of them together. So that'll take n work because I have n over 2 over here, n over 2 over here, that's n. And then we do the final level, which is combining these n over 2 pieces together. So that's why we have a 2n here. All right. And then we do one more level of recursion. So look at the result of what t of n over 4 is. Well, that's just 2t of n over 8 plus n over 4. And then when the dust settles, we have 8 times t of n over 8 plus 3n. So what do you think this is in general? Well, it looks like when the dust settles, it's 2 to some power times t of n over 2 to that same power. But what's that 3 over there? Like 2, 3. How does that relate to the 8 or the 2 to the 4?
Oh, the loss of power.
It's the power, right? It's 2 to the number times n, right? So it's 2 squared is 4, 2 to the cubed is 8. So it seems like our recurrence is 2 to the k times t of n over 2 to the k plus k times n for any value of k that you want. All right, so verify by induction. So what you can do is, what is the base case for an unsorted array? Well, one element. So you can that's just constant time, and then you assume up to k that this recurrence is true for all array sizes up to k. Then prove it for k plus 1 or some other condition where you know up to k. So I'm not going to go through that, and you can work on the details yourself. But it's just this this recurrence relation actually is correct. So what's the base case here? Well, we're doing these recursive calls down, right? Up to when we get to one element, right? So what's the running time of one element? It's just one. It's just O of 1, right? But so that's basically we're doing n divided by 2 to the k up to when we get to 1. So we just need to know what that k is so that we can substitute back into the original thing and then find the running time. So n over 2 to the k is equal to 1 because that's the number of recursive calls. We don't need to do any more. And so that means k is log base 2 of n, or O of log n, because there's a constant there. So it's log n recursive calls, right? So you can actually figure out what the running time is without doing the next step. So if we have n of, let's just say log n recursive calls, how much work am I doing for each of the calls? Well, I'm combining these arrays, right, of size n. So doing n work, log n times. So what's the running time? N log n. What's the running time of merge sort? It's n log n in the worst case. So that actually shows it, but another way you can do this is you can substitute the value for n over 2 to the k where n is. So t of 1 is just the amount of work you do for an array of size 1, which is O of 1, or just constant. So that's just n times, so we have n over 2 to the k is equal to 1. So that means n is equal to 2 to the k. So we can insert for 2 to the k here to be n times n over 2 to the k, which is 1, because that's what we assumed here, plus if you just substitute the values kn, so k is log n, so n times k, which is log n. So that means it's just n times 1 plus log n. That's O of log, O of n. Oh, there should be an n here. There's an n missing, but it really is n log n. So we actually proved the running time of merge sort by looking at this unraveling of the recurrence multiple times. Okay? So any questions about that? method. So this is actually a really good method for a lot of recurrences, but it won't work all the time. So we had this recurrence 2 times t of n over 2 plus n, but we may not have an n over there, we may not have a 2, we may not have a 2, because of this 2 to the k, n divided by 2 to the k, we might not have the 2's be the same. So we may have some other number in front of the t, and when we divide n divided by that thing. So there's got to be a more general way to approach these. So that's what's called the master method. So I won't prove this, but most recurrences have the form a times t of n over b plus some function n to combine the pieces together. So another way to think of this is splitting the input into b pieces, we split it into a pieces, and each piece is 1 over b, the size of the original input. Sometimes it's the same as a, but other times it's not. So merge sort has a and b to be 2 because we split it into 2 pieces, and we had 2 recursive calls. And the function to combine the result took n time. So this is what the theorem states. So I know it looks horrible, but so there are 3 cases really. So if f of n is O of this big expression, which is basically, since a and b are constants, this is just n to some constant, okay? N to some constant minus some epsilon. So it's basically saying that it has running time less than n to this constant, okay? Because of the minus epsilon bit. Then t of n is theta of the original thing. So what does theta mean? Does anyone know what that means? So what does O of some expression mean? It's the running time, but more formally, O of something means less than or equal to the thing in there, up to constants. But what theta means is exactly this running time up to constants. It can't be less. So, for example, n is O of n squared, but it's not theta of n squared because it's not up to constants the same, right? So what theta means is that it's exactly this running time times a constant, okay? So the second case is if it's not less than this running time, but it's actually exactly n to this constant, then we have another expression. If f of n is omega, so what do you think omega means then? So O means less than or equal to, theta means exactly equal to, so what do you think omega is? Greater than or equal to, yeah. So, and we have a plus epsilon there, so it's the same constant used every time, but here, now it's n to something plus a little bit. So it runs strictly longer than this n to the power. Then t of n is equal to something else, to theta of f of n. So this really handles all cases, right? So we have a case where it's less than this constant, it's exactly this constant, and it's more than this constant, okay? So I definitely don't expect you to get this exactly, so that's why it's part of the project. But an idea of why this works is because you have A pieces of dividing the input. If you look at how deep the recursion is and multiply by how many recursive calls you have, you get each of these 3 cases, depending on what f of n is, right? Because what the resulting running time for t of n is depends on f of n. So you have those 3 cases depending on f of n. But it really is looking at how deep the recursion tree goes and how many recursive calls you make. Okay? I don't expect you to understand this right yet, but it's just a really cool way to figure out the running time of an algorithm where you know how many pieces are going to be split and how much you split the input by and how much to combine. So this handles a lot of recurrences. And then if the recurrence doesn't have this form, so I'll get to one in a second, but if it doesn't have this form, the master method will not apply to that. So you'll either have to guess by unraveling the recurrence a few times, or you'll have to use another technique, again, for the project. Any questions on the master method, master theorem? Okay. So just let's just apply the master theorem to merge sort. So this recurrence we talked about is 2 to the k copies of splitting the input into 2 to the k pieces, and then kn to combine all of them. And so we have, since the format is a times t of n divided by b, we have that a and b are both 2 to the k because the constant times t is the same thing as dividing by n. And then we have f of n is equal to k of n, but for the master theorem, I don't care about constants. In terms of f of n, all I care about is what it is in terms of n. So it's just theta n. So because why is it not necessarily O of n here? Because I have 2n over 2 pieces. I gotta scan across all of it to write the new result in. So I really need to look at every single piece of the array. I can't just stop, say, like square root n of the way. All right, so it really is theta n here. So if we look back at the example of the master method, we want to look at n to the log of a over log b. So another way of saying this is log of a base b. It actually is the same value. So if we want to look at log of a over log b, so this is just log of 2 to the k over log of 2 to the k. What is log of 2 over the k over log 2 to the k? It's 1, right? Number divided by number is 1, right? So n to the 1 is n. So if we look at this, then we have f of n is O of theta n, and the function that we want to test against f of n is n. So we have the left-hand side of the if test and the right-hand side exactly the same. There's no it's not more than it's not more than n, it's not less than n asymptotically. So we know that we must apply which case, 1, 2, or 3?
2.
We must apply 2, right? Because there's no epsilon there. So therefore, we just write t of n is equal to n of log a over log b times log n. Well, what's log a over log b here? 1. So that means n to the 1 log n, which means n log n. So that's another way to prove that merge sort has n log n running time. It's just an application of the master method. I won't ask you to do this in homework, but it's just for your reference for being able to solve recurrences of this form. Okay? Cool. So other techniques, so project topic. So the way the master method works is a times t of n over b plus f of n. But what if we have, instead, the assumption for the master method is that each of those recursive calls is exactly the same size, right? It was like n over b size for each of the recursive calls. But what if we had a different size for each of the recursive calls? So like an example like this. So so we have t of n is equal to t of n minus 1 plus t of n minus 2 plus f of n. Does this look familiar to anyone? How many of you know the Fibonacci numbers? So this is actually an explicit way of saying what the value of the nth Fibonacci number is. Because the nth Fibonacci number is the n minus 1th number plus the n minus 2th number plus the amount of time, not the amount of time, but the value to combine them, which is 0. So f of n would be 0 there. But we can't use the master method, therefore, to find the nth Fibonacci number. So there's another way to do it using linear algebra, but you can't use the master method to do it directly. Another one is, so how many of you know what the median, what a median is of a list? Yeah. Right. So if we sort the list, find the n over 2, assume n is even. Find the middle value in the sorted list, right? So obviously we can do this in n log n time, right? We can just sort the list and then just return the middle element. But it turns out, this again is another project topic, you can find the median of or really any, like the kth largest element, so that the special case here is n over 2th largest element for the median. You can actually do that calculation in linear time without even having to sort, which I think is pretty cool. And this is the recurrence that you actually get out of it. So what you do is you end up splitting the array into five subsets and then recursively calling on each one. And then you effectively remove 3/10 of the list each time. And then O of n time to combine the result. So if you actually evaluate that recurrence relation, it ends up being theta n, or big O of n, which isn't quite intuitively obvious here. But again, that's for our project topic. So master method will not work on these. None of the other techniques handle these, so I included a link to other ways to solve recurrences. So if you want to do the recurrence project, this link will be really helpful for you. All right, so any questions on that? All right, so we have 5 minutes, so I just want to do a quick introduction to this last thing. So this is just another example of an algorithm that we're going to design an algorithm for, and then just see what the running time is in general. So stocks, how many of you own stocks of some kind? Okay, cool. So obviously we want to buy stocks when it has the lowest value and sell when it has the highest value, so we get the maximum reward, right? But obviously that's quite unpredictable, right? The stock market can go up and down, and we can't really predict the future. So suppose we're clairvoyant, right? So hopefully I'm not clairvoyant, because if I was, I wouldn't be here. I would be doing stocks right now. Let's suppose that for a particular stock, you know the price at any point in the future. So what I want to know is what's the best time to buy stock and then when to sell, right? Because that's a good thing to figure out. So what this translates to is if you model a list in terms of the day-to-day change, so maybe like the first day it went up 50, so the first entry would be 50. Then maybe it went down 100 the second day, so second entry would be 100. So I want to find the sublist in this list such that the sum, the contiguous sum, because we can't pick elements as we want, the contiguous sum is maximal, right? Because the start of that period is when I decide to buy stock, and then the end when I say that that's the maximal sublist, that's when I want to sell my stock. Okay, when should we buy and sell? Buy when it's lowest, sell when it's highest. So obviously, if every single element of the list that we're considering is positive, then just take the entire list, right? Because if you take anything less, then you might get less. But so we need to have some negative numbers in there to make this interesting. So we'll think of the current stock value starting at 0, and any value is positive, that it goes up as positive and goes down as negative. Okay. Yeah. So equivalent formulation, give a list of integers, find the contiguous sublist that has the maximum sum. If the elements are positive, just take the whole list. So what's a brute force way to do this?
Check values for every single element in the list.
Well, right. So I need to look at every single possible sublist, right? How many possible sublists are there? Well, I need to know a start and an end, right? Well, how many ways are there to choose 2 elements out of an n list? About n squared, right? It's n choose 2, which is slightly less than n squared, but yeah. Could we have an exponential number? No, we just need to know the start and end. So choose 2 distinct dates, keep a record of the pair of dates that have the highest sum, and then return the sum of there. All right, so any questions on this? We'll return to this tomorrow. Okay, cool. I'll see you tomorrow.